Hello everyone, welcome back. Today we're talking about the last type of integral that we'll learn about in our class, which is called a flux integral. Just like with scalar surface integrals, there's a lot to say here, so let's get into it. Okay, so in our class, whenever we're talking about flux, there's going to be a vector field involved and there's going to be a surface involved. And the question that we're going to be asking is, how much is the vector field flowing through the surface? We'll be trying to answer the question, how much does this vector field, 0, 0, negative z, flow through the paraboloid z equals x squared plus y squared that lies between 0 and 1? So let's go over to GeoGebra for a picture. Okay, so here's a picture of the paraboloid that we're working with and the vector field. As you can see, if we look at it from the side, this is the vector field 0, 0, negative z. All the vectors are pointing in the z direction, and when z is positive, they're all pointing down. And their magnitude increases as z increases. So the question is, how much is this vector field flowing through this surface? And we want to be able to quantify that as a number. Now, it turns out that this is a situation sort of like what we had with line integrals, where I actually haven't given you enough information to actually answer that question. Because we could be asking, how much is the vector field flowing down through the paraboloid? In other words, from the yellow side into the blue side. In which case you'd say that should be a positive number because it looks like the vector field is pointing down through the paraboloid in the direction from the yellow side to the blue side. Or we could be asking, how much does the vector field flow upwards through this paraboloid from the blue side to the yellow side? So we're going to have to do something like what we did for line integrals. In order for a flux integral to make sense, our surface has to come with an orientation. And when we're talking about orientations of surfaces, what we mean is we're specifying which direction through the surface is going to count for positive flux. So if you imagine your surface having two different colors on either side, like this one, you would say one of the orientations would be from blue to yellow and the other one would be from yellow to blue. For our example, we're going to compute the flux of this vector field through this surface, where the surface is oriented from blue to yellow. So you'll see while you're working with this stuff that we have a language that we use to specify how a surface should be oriented. We'll say things like oriented upwards or oriented inwards. But that's one of those things that you'll get a little bit more used to with practice. For now, we're going to go with this surface oriented from the blue side to the yellow side. And I'm going to abbreviate that for this surface by saying that it's oriented upwards. Okay, so back here I've added a note that whenever we're trying to find the flux of a vector field through a surface, we need to be specifying the orientation of the surface. So for our surface in question, I'm going to say we're orienting it upwards. And you'll see in a second how that factors into our computation. So before we get into computing it, I just want to note that the notation for a flux integral looks like this. And we're going to write it as a double integral with the surface as a subscript. And we're going to write the vector field dot ds, and the s we write with a vector hat on it. So this kind of looks like the notation for a scalar surface integral, which we wrote as a double integral over a surface of just a function, and then we wrote d capital S, where the s didn't have a vector hat on it. The idea is we're still kind of computing an integral over a surface. It's just now that the integrand is a vector field. And you'll see why we're writing a dot here in a second. We're going to be taking a dot product of the vector field with the unit normal vector coming from the surface at each point. And that's sort of what's meant to be represented by ds with a vector here, is the normal vector. Okay, so that's the notation for a flux integral. You'll see these all over the place in physics and engineering. They come up when you're computing volumetric flow rates, like how much a fluid is flowing through a membrane, and they come up a lot in electricity and magnetism. In this video, we're going to focus more on how to compute them rather than how to apply them, but if you're taking a course in physics or in engineering sometime in the future, you'll very likely see these. Okay, so now let's get into how to compute flux integrals. So to break down the computation for flux, let's suppose that this picture on the right is a piece of our surface, which we're going to call S, and we're looking at this point. The question that we want to ask is, at this point, how much does the vector field f point perpendicular to the surface? So let's say that f looks like this. Remember, f is a 3D vector field, so at every point we have a three-dimensional vector. And since we're trying to compute the net amount that the vector field is flowing through the surface, what we're really interested in is how much does this vector field point perpendicular to the surface, which really means how much does it point in the direction of the normal vector to the surface. So here's that vector, And we're going to call that n with a hat. So for us, for this lesson, n hat is going to be the unit normal vector to the surface. And it's important to note that this unit normal vector isn't the same vector throughout this entire process. It's a different vector at every point because we have different perpendicular directions at every point. So again, we're trying to compute how much f points in the direction of n. That is going to be approximately this length here, the length that you would get by taking the vector projection of f onto n and finding its length. So all of that to say, at every point, what we're trying to compute is the scalar component of this vector field f onto the normal direction to s. Okay, now remember maybe from a while ago that if we want to find the scalar component, which you could also write as just the magnitude of the projection of f onto n, we take the dot product of these two vectors, and then we divide by the magnitude of the vector that we're projecting onto. But since n is a unit vector, this is just f dot n. So in summary, if we're trying to compute how much f is flowing through this surface, at every point we're going to compute f dot n. That's going to be a number, right? This is a scalar. And then we're going to add all of these values up over the entire surface. So this actually leads us to a useful way to define flux. We're going to define the flux integral of the vector field f through the surface S to be a scalar surface integral over S of that scalar component f dot n ds. So again, this is the notation for a flux integral, and the way we're computing it is defining it as a scalar surface integral. Okay, a couple things about this. First, I told you that the orientation of the surface was important, and you might be wondering, how does that fit into all of this? Well, when we picked this normal vector n, we actually had a choice. We could have picked the one that I've drawn here, or we could have picked the normal vector that points in the other direction, which in this picture is down. So the way that we're going to take the orientation into account in this definition is that we're going to say that this unit normal vector n has to point in the same direction as the orientation of the surface. And the second thing is, this definition in terms of a scalar surface integral doesn't give us a super nice way to compute flux. We'll see in the second video that actually keeping this definition in mind is useful sometimes, because sometimes you can make an observation that lets you compute this f dot n hat very quickly, and that lets you compute the flux integral very quickly. But in general, we need to do a little bit more work before we have a nice way to compute a flux integral using this approach. So let's get into that now, how to actually compute a flux integral. So if we're going to compute a flux integral, we're still going to go via that definition that we just wrote down, which is that the flux integral of a vector field through a surface is a scalar surface integral of f dot the unit normal over the surface. But let's break down how you would actually compute this scalar surface integral. Remember, to compute a scalar surface integral, the first thing to do is to parameterize the surface. And we'll say that the parameterization is called r of uv. And then from this parameterization, we compute all of these things. We compute r sub u, r sub v, ru cross rv, and then lastly, the magnitude of ru cross rv. And then the last thing that we do when we're evaluating a scalar surface integral is that we actually evaluate a double integral over the parameterization domain of the function, which I'll leave a space here because we haven't really said what that is, the function written in terms of u and v times the magnitude of ru cross rv du dv. So that's how it goes. In the past, we've written f of r of u comma v. Now, that was when the integrand of our scalar surface integral was called lowercase f. Now our integrand is f dot n. So what we should really have in this space is, in parentheses here, we'll just say f dot n in terms of u and v. Now, let's unpack this a little bit. Off to the side, if we want to compute f dot n in terms of u and v, what we're going to do is actually write these separately in terms of u and v. The vector field, remember this is f of x, y, z. If we're looking for the value of that at the point r of u, v, we can just write that as f of r of u comma v, which means take the parameterization, its components x, y, and z, and just plug them into the vector field. To find the unit normal vector in terms of u and v, let's just go back to this computation here. And remember that for parameterization r of u, v, The partial derivative with respect to u and the partial derivative with respect to v, those are both tangent vectors to the surface at the point r of uv. That means that their cross product, ru cross rv, is going to be perpendicular to the surface. So actually, this is a normal vector to the surface. And so if we're looking for a way to express the unit normal vector in terms of u and v, we can take this vector and divide it by its magnitude to make it into a normal vector. Now, actually, we need to be careful, because remember that this surface that we're doing a flux integral over comes with an orientation, and this unit normal vector needs to be pointing in the direction of the orientation. So the way we're going to take that into account is saying that actually we should use plus or minus this vector ru cross rv, and you figure out whether to use plus or minus based on whether or not ru cross rv points in the correct direction. And I'll show you in a second when we do the example what that means. Okay, so now we have a way to write f dot n in terms of u and v. Now, what's going to be really nice is that when we take this yellow expression and write it here for f dot n in terms of u and v, what's going to happen is this magnitude of ru cross rv and this magnitude of ru cross rv are going to cancel, and our formula is actually going to end up being not that bad. So what we end up with is a double integral over the parameterization domain of f of r of uv dot plus or minus ru cross rv over the magnitude, because it needs to be a normal vector. So that's just the integrand written in terms of u and v. Now this magnitude of ru cross rv is there because we're computing a scalar surface integral. And then we have du dv. And again, these two things are both scalars, and so they'll cancel. And so what we end up with, I'll write it here in a different color, is the formula that we'll use to actually compute flux integrals. So just like with scalar surface integrals, we're always going to have to parameterize our surface first. And then your integral will be over the parameterization domain. You'll have f of r of uv dot plus or minus ru cross rv. And again, the plus or minus is based on how ru cross rv relates to the orientation. And then du dv. So there you go. Anytime you can parameterize a surface, you can compute a flux integral of a vector field over that surface using this formula. So lastly, let's do exactly that. Let's compute the flux of this vector field, 0, 0, negative z, through this surface, z equals x squared plus y squared, and actually just the portion of it that's between z equals 0 and 1. And again, remember we decided that our surface was going to be oriented upwards from bottom to top. So when we compute ru cross rv, we're going to have to check that it's actually pointing in the upwards direction. All right, the first step was to parameterize the surface. I'm going to use the parameterization where u and v are like r and theta. So we have u cosine v, u sine v, and then this is z equals r squared. So this would be z equals u squared. My parameterization domain, u goes from 0 to 1 because we want z to go from 0 to 1, and v is going to go from 0 to 2 pi. Next, I need to compute ru and rv, the partial derivatives. And then I'm going to compute ru cross rv. And now remember, this is going to be our normal direction. We have to make sure that it points in the direction of the orientation of the surface. And to figure that out, notice that on our parameterization domain, u is always non-negative. And so what that means is this vector always points with a positive z component, which means that this is a vector that points upwards more than it points downwards. So I'll just note again that when we say upwards pointing normals, we don't mean that all of the normal vectors are literally pointing straight up like 0, 0, 1. It means that of the two choices of normal vectors at each point, we're taking the ones that are pointing more upwards than downwards. So since we chose this parameterization, the normal vector that we got does point more up than it points down. And so it is pointing in the correct direction for the orientation of this surface. I'll just take this opportunity to note that if you had used a different parameterization, such as r of uv equals u comma v comma u squared plus v squared, then you should try it. You'll get a normal vector that points downwards. I think the z component ends up being -1. And in order to make that work with this orientation, you'll have to use negative ru cross rv in your formula. Anyways, now we're ready to compute the flux integral, which again, the notation for it looks like this. And the way we're going to compute it is an integral over the parameterization domain. So we're going to say v goes from 0 to 2 pi, u goes from 0 to 1. And then we have f of r of uv, which we get by taking our parameterization and calling the x, y, and z components x, y, and z and plugging them into the vector field. If we do that, we get 0, 0, negative u squared. And then we're taking the dot product of that with ru cross rv, which again, we're not negating because our orientation worked out. And that is negative 2u squared cosine v, negative 2u squared sine v, u. And then we have du dv. And evaluating this dot product, things simplify a bunch. We only have negative u squared times u here. And so we end up with the double integral of negative u cubed du dv. Now you could do this double integral really quickly on your own. If you do it, you'll get negative 2 pi over 3 as the answer. So this number represents how much this vector field flows upwards through the surface. And it's negative, which means that actually the vector field is flowing in the opposite direction of the orientation that we specified. Going quickly back to GeoGebra, the value we computed is how much this vector field flows upwards through this surface. But since the vector field is pointing down, that's why we got a negative, because it's flowing in the opposite direction of the orientation. All right, that's the end of this video. You're now ready to go practice computing flux by parameterizing surfaces and using that formula. But since flux is such a complicated topic with lots of little different pieces, we're actually going to be spending 2 classes on it. In the next video, you'll see that sometimes we can use that definition of flux as a scalar surface integral to compute flux without ever parameterizing the surface. All right, I'll see you in that next video. Thanks for watching.